EC 111, Lecture 1, Set 5. We're just going to go through some digital design basic. Hopefully you've all seen the individual circuit design components that are combinational, such as AND and NOR gates. I'm just listing some of them here. But most of the realistic circuits are actually more than just combinational components. They have also memory elements. And this means that we have mixture of the combinational elements I just showed on the previous slide, for example, and some storage elements. And typically in a modern sequential circuit, most of the memory elements are synchronized using one clock, and then combinational parts are transforming the values that are stored in this storage element in one clock to the values it should be in the next clock. The storage element that we will be using in the designs here are called flip-flop, which is basically a storage element that has an input D and output Q as shown in this picture, but there is a notion of the clock that synchronizes all the memory elements in the circuit. For the practical purposes in this class, we'll be talking about edge-triggered flip-flop in the example shown here, and mostly in the assignments and projects of the class as well. We'll be talking about a flip-flop that is sensitive to its rising edge. What that means is that, as you see in the timing diagram on the slide, there is a clock that is a periodic element. There is input D, which is going up and down as without any synchrony to the clock. But what we do, at the output Q is we only sample this value of D at the rising edge of the clock. So as you see here, if D changes in the middle, we don't really record it at the Q unless another rising edge comes. For example, here in the rising edge, what happens is the Q value is sampled again and it goes to 0, but the changes in the middle that are not on the rising edge are not recorded here. Hopefully you've all seen a timing diagram. This is a simple timing diagram for a flip-flop circuit. If you're going to design a piece of hardware, what you want to have is really, you want to be able to read it again later. You want not just you, but if it's a complex design, you want someone else to be able to read it and understand it. It shall be simulatable and verifiable. You want even the software people to read it, but I have to emphasize that writing hardware is not exactly writing software, because we want this to be a functional piece of hardware and artifact which has a physical implementation. So you want this to be synthesizable into actual physical gates, which is something you may not really need in software, as you will see go through the examples. Now, how could you represent hardware that is scalable? Let me go through an example and show you step by step how this can be done. Here we have a small design, a half adder. Hopefully you guys have all seen a half adder before, but half adder is nothing else but two inputs, A and B, and then we have the sum and the carry out from this half adder block. And now the equations for the sum and for the C out are written in terms of the combinational logic gate. Sum is A XOR B, and output is A and B. There are different ways to represent the circuit. Here is one way to represent the circuit, which is basically a Boolean equation for a half adder. Now, I could go ahead and show this in terms of a gate. This is a schematic representation for this adder. You see the XOR and the AND gate in a schematic representation. I could also make a netlist for this, and a netlist is there are different standard formats for the netlist. I'm here just showing my own format, which is not a standard format, but let's say my format is I start with the operation. So my operation here is sum or in this case, sorry, it's not a sum, it's actually, the operation is XOR, and the input to the XOR are A and B. The output is sum. And this is only a representation for a 2-input gate. Obviously, if I had a 3-input gate, I should have come up with a different way to represent my netlist. And then, I have the AND function, which is, again, A and B, and the output is Cout. This is a netlist representation. Now, for the description language that we will be talking about, we want to go beyond this. This is better in some sense, which means that it is we can write the text file instead of drawing. But again, it may not be easily scalable or easily even readable for someone looking at it. We want to go from something kind of a little bit more functional, which the tools can help us understand. And that's what we will be doing with HDL. I'm going to go back to the slide and show you some examples of that. HDLs allow us to do textual presentation of the logical design circuits. These are not programming languages. They actually compile things to a piece of hardware, but the development chain is kind of similar to what you've probably seen in a software compiler. In software compiler, you go from a source code to assembly to binary machine code. Here, you go from an HDL source code to a gate level specification, and then you hopefully can take this and make a hardware artifact. Using an HDL can greatly enhance your design capabilities. It can make things easy to write and edit, can make working in a team possible. It can make things compact, and also it allows you to use computer-aided design tools that you would not otherwise be able to use easily. But you still need to have an understanding of the design phases. So using the tool does not remove the need for a designer. You need to understand the designer, and design may be sometimes a work of art. You need to get experience doing that by doing a lot of design examples and get your hands on the tool and the design. The other thing to know about the hardware description languages is because it is compiling things to a piece of hardware, and there are two usages of that, as we've seen earlier, synthesis and simulation. What happens is that you need to understand that there are things that we can do in simulation that we are not exactly synthesizable into hardware. For example, you could have constructs that you could use for testing or for verifying each of your blocks that you don't really synthesize them once you ship the design to or once you use this to program a piece of hardware. You may, for example, use something like a printf, which prints the output for you, but you don't really have that in a synthesis environment that synthesizes things to hardware. This is only for simulation because you want to see the inputs and the outputs. You may want to load files to your to your simulation and output the output to a file, which may not. Some of these constructs are not useful. So, in brief, there are many more language constructs that are used for simulation that are not having an actual physical value during the synthesis. Synthesis is really about making hardware. So every time you write a piece of code, you're generating a piece of hardware. With that, we will be talking about the next set, about the very basic system Verilog code equivalent to a hello world in the C programming language.